And Heffernan will be talking about self-force waveforms for EMRIs.
Hi, thank you for having me. I'm just going to try to share screen. Okay, is that working?
Yes.
Yes, it is.
Okay, perfect. Okay, well, thank you for inviting me to speak. Today I'll be talking about self-force and how it works for waveforms for EMRIs. And in general, I'm just going to give an overview of the self-force program, and then my particular work is focused on the Detweiler-Whiting singular field, so I'll talk a little about that. Okay, so to begin with, the motivation for self-force is what we call EMRIs, extreme mass ratio and spirals. And if at any point during this talk you forget what an EMRI is, you can see it just here in the corner of the slides. So the idea, I'm just going to move this down here. So the idea is you have a little black hole that's evolving and not plunging into a very big black hole. Why these are of particular interest is because it is a little black hole. It kind of holds its own against the big black hole. So you end up getting tens of thousands of orbits. So you can track these for quite a long time. And we expect these to be at the center of our galaxies where the supermassive or massive black holes are. Okay, so you'll be hearing me talking about EMRIs, and this is our EMRI. Okay, so, okay, this is starting to work. Okay, why these are of extreme interest is it is a source for LISA, the future space-based gravitational wave detector. And they're precision astronomical probes, because as I said, as this little guy is going to do tens and thousands of orbits, the variance with all the parameters you're going to measure is going to be the inverse of that. So if you have 10,000 orbits, that means you're getting an accuracy of 10 to the minus 4, 10 to the minus 5. And this is great. This means we're going to get spin. We should be able to, if we detect these parameter estimation, you're going to get spin to 10 to the minus 6, 10 to the minus 7. Your red-shifted mass, 10 to the 6, 10 to the minus 4. Distance and source masses, obviously you have the distance redshift ladder coming into play. So unless you know exactly what galaxy you're in, then you're going to lose some accuracy, which is why these are to a lower accuracy. Okay. Also, you're going to get environmental information. There should be information if you have accretion disks in place. Sky location will be accurate enough that hopefully, again, because these are supermassive black holes and they may have accretion disks, you would hope that maybe EM people will be able to see them and you could have multi-messenger. And remember, it's not like a flash in the sky. These are sitting there for months. You can use them to detect actually these supermassive black holes. Also,
hi, Anna. Just sorry for stopping your talk for a second. Are we supposed to see two slides at the same time? I'm just wondering.
Ah, okay. You're seeing the wrong screen. Okay, 1 second. Oh. Yeah, you're not. Wait a second.
Well, we can still read, but it's a bit small. So.
Yeah, no. Let me think if I can.
Sure. Please take it. Thank you.
No. Okay, 1 second. I know. I'll try share again. And Zoom. Okay. Okay, this here. Oh, it's not where I am. I think I have to plug it in my second screen.
Thank you very much.
No, thank you for letting me know. Okay. Where was I? Okay, yeah. So also because if we track these, you could be seeing them for months, even a year. So you could get information about galaxy and massive black hole evolution, how the galaxy evolves. There's also a lot of cosmology involved. So anyone who's heard about LISA, they might have heard that it's an extremely exciting mission for cosmologists because you can track different types of binaries at different redshifts. So you can actually try get this redshift distance ladder. So the EMRIs could be used as sirens, because again, you're tracking them for 6 months and you can be tracking several of them. So again, this could be used to constrain the Hubble constant. And then again, because you have these 10,000 orbits, you're basically tracking this little guy, and he's mapping out the space-time of the big black hole for you. So it's actually giving you a really nice map of the space-time geometry of what we expect to be a Kerr black hole. And then if it's not a Kerr black hole, we should see those deviations. So they're very good tests of GR. I'm going to move this over here. Okay. Okay, so tighter constraints on beyond Einstein, alternative theories of gravity. Okay, so parameter space. This is kind of like a cartoony picture, but it's nice and clean and clear. So if we think of binary systems, say black hole binaries, you can think of the parameter space on the y-axis here, we have how close they are together. And along the x-axis, you have the mass ratio. So are they same mass, which is kind of down along here, or do they have extreme masses, like the extreme mass ratio and spiral, which kind of come over here? So when you look at all the different methods of describing these systems, we heard Laura Bernard yesterday talking about post-Newtonian theory. Post-Newtonian theory, it is very well established, it is excellent, but of course, because it's a perturbation in the speed and strength of the gravity of the system, as the two black holes are coming closer together, it's going to break, your perturbation is going to break down. So post-Newtonian theory is extremely powerful for all mass ratios, but just at that point where you're going to merge, it's going to break down. Fortunately, at least in the smaller, the more comparable mass ratios, this is where numerical relativity kicks in and is applicable. And these actually overlap. These should be overlapping. So numerical relativity, where you're actually, you're solving the Einstein equations for a specific system at a time. So post-Newtonian, you have the answer for all systems. So super powerful. Numerical relativity will give you the precise answer, but just for one system at a time. So people are working hard at filling the parameter space there with all the different simulations and also comparing the different simulations. Now over on the right-hand side here is where self-force comes in, because as I was saying, as those mass ratios get more extreme, what you can do is apply self-force, because what self-force is, it's a perturbation in the mass ratio of the system. So if you want to do a perturbation, you always need something small to perturb in. Laura no doubt explained yesterday in post-Newtonian, it's the speed of the system over the speed of light. In self-force, same idea, except our small perturber is the mass ratio. And that means as long as you have an extreme mass ratio, it will be applicable for the entire, it doesn't matter how close they get, you can do the plunge, you can do the merger. So you have this entire parameter space coverage. Okay, so far, why haven't people been overly excited about self-force? Well, because all the gravitational wave detections or the gravitational wave astronomy that's currently going is in the LIGO, Virgo, Cagra. So our ground-based detectors. But luckily for them, post-Newtonian theory and numerical relativity have that part of the parameter space covered, although there's issues getting into eccentricity and spin precession, but for what they can see now, they have a good handle on things. And like I said, in the near future, I think it's going to be a launch in 2034, currently, maybe 36 actually, will be the, sorry, this should be three lasers, will be the LISA gravitational wave mission. So this is led by the European Space Agency, but NASA is also a major partner. But ESA is the primary partner, the primary organizer of it. So what's super exciting about this is it's going to be 3 spacecraft bouncing lasers around both directions. You want them to also be able to control your noise. And this works with 3 individual interferometers. So you don't have that perfect right angle, but you have 3 60-degree angle interferometers with a spacecraft kind of being the hub of each one. So now you have 3 interferometers in space following the orbit of the Earth. I think it's going to be tilted at a 6-degree angle, and it's going to be an equilateral triangle itself. And these then should hopefully detect. Actually, they'll also detect this side of the parameter space too, because they'll be able to see massive binaries. So when you have two supermassive black holes, and when you have galaxies colliding, then you have those supermassive black holes at the center of those galaxies colliding as well. And they're going to be comparable mass. So all this work that's been done for LIGO is going to be very applicable to LISA for those massive binaries. However, for this part of the parameter space, post-Newtonian still very and really good for checking that the self-force results are correct in this part of the parameter space, but you do need self-force to get down here. Because again, like I said, post-Newtonian will break down as you get closer to merger. But numerical relativity has problems with the different length scales, so that also breaks down. I think one or two groups have done maybe a mass ratio of 100, but there wasn't a good resolution on the errors. And I think then the other highest one is being a mass ratio of 18. That was actually done by people here in the Balearic Islands. Anyway, okay, so this is our parameter space, and this is why we all love self-force, or why now self-force is beginning to become relevant, because we have the space-based mission coming up in about 10 years. Okay, so this is the self-force is place to shine, and obviously their job, like all the other theories, is waveform. Sorry, I should mention in this picture, because I know people have also talked, obviously when you want to do any data analysis with waveforms, you need something that kind of can smoothly cover the parameter space. So that's where you have things like effective one body and the Heffernan models. I'm not saying they're not important, but they take in the information of post-Newtonian self-force numerical relativity. So that's why I'm focusing on those. All gravitational wave astronomy actually uses EOB and Heffernan. Okay, so waveforms. Okay, so what you need for a waveform. For a waveform or self-force, we need, a lot of time you might have heard of first order or second order. So it's just literally what order in the mass ratio you are. So you need a highly accurate first order and you want it to be eccentric, and you want to be able to incline to the equatorial plane. Equatorial plane is a lot easier, of course. The minute you incline it, it becomes a mess. But that is kind of what you're expecting in the center. And when we calculate the self-force, we're kind of calculating a little snapshot. We're just saying how much this thing is moving off its geodesic. So then you have to calculate that at every time step. So you have to evolve the orbit. So a lot of work has been done towards that. So this was some work in 2019 by Chris Barry, using, I don't think it's just a geodesic. And then people have then put in the first order and been able to evolve that as well. Okay, the last thing you need is second order. And this is probably the least developed part of the self-force program, but they have only in the last 2 years actually got the first result out, which means self-force only got its first full waveform out 2 years ago. And this was that waveform. So if nothing else should convince you today about how amazing this is, this is the picture, because this is a mass ratio of 10. So sometimes you hear post-Newtonian people say, when they first started doing post-Newtonian and comparing it to numerical relativity, they found that it did better than they expected. Where you thought it would break down, actually got a little better. Not that it got better, but it worked better than anticipated once they were able to check against numerical relativity to see where it would break down. And basically the exact same thing has just happened in self-force. So we in the self-force community, we're always talking about EMRIs, extreme mass ratio in spirals. When we got the first waveform out, which was done by Barry Wardell and several collaborators in 2021, what they actually found is it matched very well for mass ratios even at 10. And what that means is if you look at this parameter space again, I'll just put this down here, is it's not just EMRIs, but also you might have heard of EMRIs, intermediate mass ratio in spirals. And these are very interesting because an intermediate mass ratio has to have an intermediate mass black hole. And these still haven't been detected. Well, at least my understanding is the astrophysical community hasn't accepted that these have actually been detected. We have the more stellar mass black holes, and we have the supermassive one at the center of the galaxies. And people think one grows to the other, but no one's seen anything in that middle space. And you're actually seeing these kind of that's mass ratios of maybe over 100. So we can see self-force will apply there. But even at that, in LIGO, they're starting to see mass ratios of in and around 8 or 10 sometimes. So actually, all of a sudden, self-force will be applicable to the ground-based detectors, and even more so as they upgrade more, right? Because as the ground detectors get more upgraded, they become more sensitive to these higher mass ratio systems. So currently in LIGO we're in 04, but 05, you would expect to see more mass ratios, extreme mass ratios. So this was a very surprising result that people weren't expecting it to work so well. Okay, another game that's been played that I hinted to earlier is in this other part of the parameter space where you overlap with post-Newtonian theory, was actually comparing with PN. And this actually was very fruitful because, as I said, we only got the first waveform out 2 years ago. Before that, when you calculate the self-force, it's very gauge dependent. So, which made a lot of people uneasy, but it meant that we started comparing with post-Newtonian people and trying to come out with other gauge invariant quantities, right? Because the waveform is a physical entity, you're not going to have any gauge dependence. Great, but we didn't have the waveform. So people started going, is there any other gauge invariant quantity that we can calculate and compare with PN? And this developed into a huge game where people started coming up with the Detweiler redshift. And again, beautiful comparisons. And that was really good because that was 10 years ago, and it clarified for self-force people that what we were doing was correct. We hadn't made some weird assumption that didn't apply. And on the other end, for certain particular systems with mass ratios, we were able to read off unknown PN coefficients. And maybe Laura touched on this as well. You have people playing this game with Post-Bukowski and also EOB, where people are reading off different coefficients. Sorry, not EOB, effective field theory. And then, of course, this was used to calibrate EOB, the effective one body. As I said, covered the whole parameter space, but also phenom. Okay, so that's our parameter space. And hopefully I've sold you on the importance of self-force. Oh, okay. So what is the self-force then? So back to actually what do we do? So we perturb the metric in the mass ratio. How we go about doing that? Again, you have your little black hole. And so I'm now going to draw its world line over here. So here's my little black hole. And it's on a time-space axis. Okay, so it's got a size, so it has a world tube. And then it has a nearby zone. Now in this near zone, what you normally say is, if I'm near that little black hole, I don't really care about the big black hole way over here. I'm more concerned with the little black hole near me. So you kind of say, well, the space-time here is dominated by the little black hole. That's what I care about in this area. Now, because there is another black hole in the vicinity, we can't ignore that. But the big black hole will be a perturbation to that little black hole. And epsilon here we have to the mass ratio. In the meantime, if I'm super far away from this little black hole, like say the Earth and our detectors are, it would be the big black hole that's really overriding what the space-time is going to look like, right? So you can imagine if I'm somewhere over here, or in this case here, the little black hole I'm not so concerned about. It's the big black hole that's really controlling the geometry of the space-time. So in that scenario, you say, well, the metric here is going to be the big black hole. There is a perturbation for the little guy because he is there and he is affecting space-time. And then what you do is you think of a buffer zone. Okay, at some stage, these two metrics have to meet and agree at a boundary. And you say that has to be within the curvature. And then you solve for things in the buffer zone. So this was done, I think, in 1999 for the first time. And this was just to get the equations of motion, which then became known as the Misataka equations. The Mista was because it was Mino, Sasaki, and Tanaka. And then you have the Kwawa, which stood for Quinn-Wald, because it was two independent calculations came out at the same time, which is brilliant because they used completely different methods and they arrived at the same equations of motion. This whole system I've described here was actually the Misata way of doing it, the Kuawa, the Quinn-Wald. I will talk about a bit more later. But in general, this is the idea of how self-force works. Okay, so keeping that in mind, how do we get waveforms? So we think about a zero order. I'm sure everyone here is very familiar with geodesics in Kerr space-time. So that's what your zero order is. And as I'm sure lots of people are aware, your geodesic for Kerr space-time is characterized by three constants. You have E, which is your energy, your LZ, which is your azimuthal angular momentum, and your Q, which is your Carter constant, which is related to the orbital inclination. Now, these associated with also your R theta phi, you have three phases. And the three phases will have frequency or omega, which is derived from your constants. And again, this is all very well established and solved for. And you get these very nice pictures like this one by Steve Jessica. Okay, so this is what happens in zero order. And then what we say is because this is a black hole, it's not a test mass particle, right? It does have mass. Therefore, you kind of say, okay, well, we have the big black hole and we have this, the mass is going to push me off a test mass geodesic. And that's why we call it the self-force. Because you're forced off the test mass geodesic due to your own mass. So self-force. Okay, so how do we add the self-force? Okay, so the way this has now developed is you might hear of multi-scale waveforms. And the general picture is, based on the periodic structure that we already have, you want to kind of keep and maintain that. So what you look for is good perturbed variables for the orbit. So again, they're the same as before, but now I've got a tilde on them because they are perturbed. And sorry, this is describing the orbit of your smaller black hole. Now, of course, because you have this big black hole here, your system parameters are also going to have the mass and the angular momentum of the big black hole. So you have these two extra parameters coming into your system's equations. And then similar to before, your phase frequencies will be determined. You have an ODE that it is dependent on the system of parameters. Now, the evolution of the system of parameters is slow. So we have the zero order and the first order. Now, just to be confusing, now I'm talking about adiabatic orders, but I'll explain how that relates to when we talk about first and second order self-force. You have your geodesic, then you have your first order self-force, and then you have your second order self-force. Now I'm just saying, when we have a system of parameters, we have a base forcing term, and we have a first order. And these are completely dependent on these system parameters. So you have this nice separation. And also what is notable is that in front of here, these are all of order of epsilon, which is of the mass ratio, which by design is small. Whereas your phase frequencies are order 1. So you have two different timescales. And as the mass ratio is always going to be very small, we then look at multi-scale waveforms. So multi-scale waveform then, and again, this probably looks similar to other things you've seen in the last few days. You have your amplitudes, which are the sum of your first and your second order. And then you have your phase factor. And now the phase factor, we know is going to evolve a lot faster than our system parameters. So you have a slowly evolving amplitude and a faster phase factor. And then this is taken advantage of in how to determine these things, how to calculate the waveforms. So in actually carrying this out, oh, it's gone off the page. In reality, what people do is they solve the Einstein field equations for these amplitudes and the forcing functions, which are all functions of just these system parameters. No phasing in here. So you have your system parameters, and you can calculate that offline for a grid. So just think of all your different systems and calculate this for an entire grid. And that can all be done beforehand. And then what you do is you do have to solve the ODEs and for the time evolution. Okay, so once you have your phase factors in your HLM, these are going to tell you how your phase frequency, how your phase evolves. And that is what's done online and gives you out your orbit. This has been highly optimized by Michael Katz and several collaborators to give the fast EMRI waveforms. So if anyone wants to look at what a waveform looks like or play with it, there's this nice package called Few. If you just Google fast EMRI waveforms, it should come up. And there's all this, I think it's a Python package that you can run, and it will produce these waveforms in 10 to 100 milliseconds. And what's great about that then is that these waveforms are already being used to do data analysis and try to figure out what actually Lisa could see, or what parameters we can read to what accuracy. And then, as I breezed over earlier, in this equation, we have these forcing factors. So this is like the first order self force. If you just have the dissipative piece of it, that will give you this the zeroth order forcing term. It's the geodesic plus the dissipative piece of the F1, the first order self force. But we think we're told by data analysis people, most likely parameter estimation will need the next order. And for that, you need the conservative piece of the first order self force and the dissipative piece of the second order. And because the first order is coming in at this earlier power, it means you need to know your first order more accurate to your second order. I think people are saying we need to know this like 5 or 6 digits. And the second order, you don't need to know as well. But it's a very complicated calculation. Anyway, so this is how we get the waveforms. All right, where we currently stand. So this is a picture I took from the Lisa waveform white paper, which I was one of the coordinators of. But a big shout out to Josh Matthews, who was the one who actually produced this. So this is kind of where we are right now for self-force waveforms. So that's zero term that I talked about, the adiabatic, which needs the dissipative part of self-force. And the post one adiabatic needs the conservative first order, and the second is dissipative. I didn't really want to go into spin effects, but they do come in at that same order. Okay, so for the first order self-force, and this is mainly where all the self-force community has been concentrated for the last 20 years. And well, in these two parts. So this is all very well developed and we have all the pieces. Now you could say though, when those fast EMRI waveforms I showed earlier, like all the pieces are there, but they're not all included in that waveform package, as in, when we develop self-force, first of all, obviously we look at Schwarzschild, it's non-spinning. And first of all, the easiest thing you can do is a circular equatorial orbit, and you go to eccentric. Once you have the under wraps, then you go to Kerr. Things get a lot more complicated, so you start again with your circular. Then you do eccentric or equatorial, and then you do generic, so which means you tilt or incline your orbit. And going from here to here, I can tell you, that took I think the first eccentric equatorial calculation, snapshot calculation came out was in 2012. And generic, I think, was then 5 years later. And then also resonances. You can get resonances where you will actually see this jump in angular momentum. And so you have to keep track of those as well. Okay, so for adiabatic, we're looking pretty good, but to do parameter estimation, we need post 180 back. So there we have Schwarzschild very much under control. So 1 tick means snapshot calculation. So that means you've actually just calculated the self-force. 2, you've calculated the in spiral, driving it in, and 3, you've evolved your waveform. So you can see for Kerr, we're not as developed as we would like to be. And we need Kerr because you expect your black holes to be spinning, or your supermassive black holes to be spinning. So, but we have 10 years, so no panic yet. But basically, we need lots of ticks here. But also, if you look at second order, like I showed you that waveform of the second order self-force, that was circular Schwarzschild. So it's circular, non-spinning. And that only came out in 2021. So they're also now trying, the next step is I think they're concentrating going to Kerr more than eccentric to even get it circular, because then they could start being used in the ground paste detections. But you still see there's a lot of work to be done here on second order. And like I said, for some of these, it took years, 5 years to go from here to here. So, but people are confident we'll get there in 10 years. Okay, and then you have your spin effects, conservative and dissipative, also coming in this order. And again, the ones where they're just done for spin or anti-aligned are ticked separately with the asterisks. And this was all developed actually very recently in the last few years. Okay, so that's a snapshot. So, okay, so we still have some time. So what I wanted to do then was actually bring you through how we actually calculate the self-force. So, like I said, it's a metric perturbation. So sometimes actually the idea is easier than people think. So what you do is you perturb, because we concentrate in the far zone, and we perturb the background space-time. So in reality, you have an effective metric, which is really what's going on. We don't know how to solve that, so we linearize, right? We say, okay, well, I'll have a Kerr background, I'll have a Kerr black hole in the background, and then there's going to be a perturbation, and that perturbation is going to be around the size of the mass ratio. And then I'll see second order. Okay, and we have our Einstein field equations. And again, when I use this typeset here, I'm talking about the full metric that we then linearize the calculation. Okay, so everyone's familiar with the Einstein field equations. If we perturb them, and I'm just going out to first order now. Okay, so you have your base Einstein tensor, and then you have the perturbation of it, and then you have your source term. Okay, if we say it's a Kerr metric, well, that's going to be 0, and we're just going to have this perturbation here. And again, you can just throw this into, if people want to do X tensor in Mathematica, or you can just do it by hand, but it's a very straightforward calculation in perturbing your Einstein metric. And of course, you get your Lambertian, so the beginning of a wave equation, and your Riemann tensor, and all these. Okay, but then we pick the Lorentz gauge, so we set a lot of things to 0, and we're left with a wave equation. So basically, when you do the self-force, and you just say there's a perturbation, just like in gravitational waves, you have a wave equation, you have your Riemann tensor, and you have your source. Okay, so to get my stress energy tensor, I can get the action of the small particle, and I vary it, and I get my stress energy tensor. Okay, this looks quite complicated, but as we go on, I want to get the resulting equation of motion. Okay, so I have my stress energy tensor, and as we know from conservation, if I get the covariant derivative of that, it's going to be 0. Okay, so this looks complicated, but it's not actually. I get the covariant derivative, so this is all in the integral, right? So I just have to hit X, so I hit it here, and then move that out using several formulae over to hit this. So I'm just moving my partial derivative over here. And then if I take the partial derivative of this, I actually, okay, you can pull out this and you get basically this equation here. Okay. What's very nice about this setup and why I bother showing it is because you hit a covariant derivative, you can turn it into a partial derivative, then you move it over to the other side, and then you just rearrange this to look like this. Where K is, you've just taken the derivative of your square root, and you've got your derivative then of your your 4 velocity. Okay, now is this equals 0? That means this has to be equal to 0. But if I actually write out what this d is, it's the difference between my Christoffel in this effective spacetime and my Christoffel in my background spacetime, multiplied by my z's, and then I have my kzz. So in perturbed spacetime, I mean, again, because this has these h's have an epsilon by them, so you can just do a Taylor expansion, and this is just going to be -1/2 by your UABC. And what that means then is at 0th order, I'm going to get, so you have your k is basically equal to epsilon. So at 0th order, my acceleration is going to be 0. But at my 1st order, I'm going to get an acceleration. And this whole idea is that you have at 0th order, you're this test mass geodesic of the background spacetime. And if I keep everything in that background spacetime, what I'll find is an acceleration at 1st order of the mass ratio. And you can also see, you can rearrange these to pull out GAB plus UAB. So when you contract out with the 4 velocity, this will go to 0. So you know your acceleration is orthogonal to your 4 velocity. So this is the basic idea. So even just by doing standard perturbation of the metric and looking at the conservation of energy, you can actually get out, not surprisingly, that if you transfer everything into this linearized background spacetime plus a perturbation, you'll get a 0th order, no acceleration, because you're on a test mass geodesic, but at 1st order, you will get an acceleration. And this is the self-force, because it's caused by your mass. Okay, so that's the general idea. But I glazed over something, which is when we actually started with the stress energy tensor and saying it was described by the action of the smaller mass, what we did is we used the delta function, right? We assumed that there is a delta function in there because that's making life easy, but in reality, there's not. And we have to learn how to regularize and counteract this assumption that we introduce, because infinities are hard to deal with when you have to do numerical simulations. Okay, so the idea is to describe all this, we introduced a delta, which is a singularity. Now we need to get rid of it. We don't get rid of it, but we need to clean up any ill effects that assumption has on our system. So how we do that in flat space-time is, again, so I'll just go through flat space-time so because everyone should be familiar. So if you take the case of electromagnetism, you have a wave equation and you have 2 solutions, the retarded and the advanced solution. And your solutions are often written as an integral of a Green's function with your source term, which is singular. So these Green functions obviously then satisfy a wave equation with a source by a delta. And the idea is if you have, say, the world line of a particle, you have the retarded solution is basically that this particle in the past has emitted to this field point. Because these are the 2 points. Okay. The advanced one is the opposite. If something came from that field point and hit you in the future, which is kind of called the advanced solution. So you have your retarded and your advanced solution. All sourced by a singularity. So to take care of the singularity, a lot of time what people said, well, okay, well, realistically, we're talking, this is kind of in the future. So the more causal relevance is the retarded solution. This has been emitted from my particle in the past and accepted by or received by my field point. So what we do is if we take the retarded solution, we say, okay, well, in reality, what's happening here is there's a regular part, which is kind of the real physical one. And then there's this singularity structure that I've kind of introduced that I want to get rid of, but in a way that it doesn't affect the motion or any of the equations. And the way they do that in flat space-time is quite simple. They just get the average of the retarded and the advanced. So if you think about it, this is incoming, this is outgoing. If you sum and average these, you can kind of think of almost as a standing wave, right? The incoming energy is equal to the outgoing energy. So it's not going to affect your system of equations. Okay, and because both of these are solutions to the wave equation, then the singular field is also a solution of the wave equation. So you know it solves the exact same wave equation as the retarded or advanced. And that means then to get the regular, we just look back here and all we do is we subtract it. You have your retarded function, you subtract your singular one, which is just the average. So then your regular field is this. And what's nice about that then is if I want to get the square of my regular solution, well, I know the square of this is going to give me this, as is this. So these are just going to cancel. Their singularities will cancel beautifully, and I'll get a homogeneous wave equation. So I've gotten rid of the singularity, but by using it in a kind of like standing wave system, so I'm not affecting the equations of motion. And then to get the force from this, use your Faraday tensor, which people hopefully recognize, and get your derivatives. Okay, and then when you get the force, you have your external, and then this regular part here, which is gotten from the regular part, which is the solution of this wave equation, which you can find numerically. Anyway, so this was all done by Dirac in 1938. So very nice, it's very clean. But if you try to do the same thing for curved space-time, okay, and we'll stick with electromagnetism for now. A lot of the time we work for scalar cases and electromagnetic case before doing the gravity case with self force. Okay, so now we have a Ricci tensor in play. Again, we can just say, well, the solutions are going to have a Green's function with my source, and now I have curved space-time. So a lot of time what we think about is we use Hadamard constructed Green's functions. So this looks complicated, but it's actually not. So the idea is, wait until you have what we call the direct part and the tail part. I want to see, I think I have, yes, this is what makes it easier. So before, remember, because you had flat space-time, you just had a direct connection from, say, the particle on its world line and, say, the field point. But now that you have curved space-time, you can have radiation arriving from any time in the past history that might have scattered over curvature and arrived later. And this is done by this is countered by this step function. So the delta along sigma is the thing world function. You need to know it's 0 on the light cone. So when on that light cone, you get the direct part, and then the history is controlled by the step function, because this is negative when it's time connected, and it's positive when it's space connected. Okay, so we say, okay, our green function has the direct part that's very similar to the flat space, but also we have this kind of tail here. Similarly for the advanced, it's kind of in the future, right? Because you would have radiation coming off here and it could scatter off curvature and hit later. Okay, and again, because it's the green functions, you throw this into this, and obviously they have to solve this wave equation. Okay, so for flat space-time, this is quite easy. You're sourced by a delta. And yeah, you have you end up with just a delta sigma, right? You're only dealing with this point. But now we have this tail part coming in, which is complicating our system. Sorry, what I should also have mentioned, can I go back? Sorry, I'm back too far. So if we try to do what we did before, remember we want to try, we've introduced a singularity, we have to remove it. If we want to try do that like we did before, you're like, okay, well, let's do what Dirac did, right? We just get the average. But if I got the average of these, I now have something that depends on the entire history and the entire future of the particle. So it no longer works. We can't just get the average of the two of these and separate away. It's a mess. Okay, and that's where the Detweiler-Whiting, I have to, waiting, should be Whiting singular field comes in. So their idea was, or a nice way of thinking about it is, okay, let's say I kind of do what Dirac did. We say we get the average of the retarded advance, and we just say we have another biscalar in there that we're not sure what it is, but it has to solve this issue of not having everything depend on the future. And of course, if I subtract this away from the retarded, it means the regular part will be just half the retarded minus the advance. And again, you'll have this thing. And then you just put some demands on what H should be. And you're like, okay, well, I want it to be a solution of the homogeneous wave equation, because I don't want it to affect, this will nicely remove the singularity here. I don't want this to affect it. So it has to be a solution of the homogeneous wave equation. So when I get the Albertian, I want it to be 0. I want it to be symmetric in the arguments to keep the equations consistent. And when I'm in the future or in the past, I want it to be 0. And in the regular part in the future, I want it to be 0. So when you think of all these things that you want, actually, okay, there's more, sorry. You want it to be the retarded function when you're in the past and the advanced when you're in the future. But basically, at the end of the day, what the one thing that solves all of these is actually V, that tail term that we had multiplying by a step function. So actually, it turns out if you get the average of the advanced and the retarded, and then you just subtract away the tail, you get a singular field which completely removes the singularity, but doesn't affect your equation of motion at all. So then, remember we have our retarded and advanced are like this. And now we take, this is our singular now. We have this +1 because of the V term we've added on. And if you subtract that away from this, you're just going to get a U minus V with a step function, and you've lost your minus. So this is basically looks like this. Right? You still have your delta points here, the U and U, but now you've lost your minus. So now actually, instead of all the past and all the future, you're actually looking at where it's space-like connected to your field point. So this is something much more easier to calculate than something that depends on the entire history, entire future. And this is the Detweiler-Whiting singular field. I'm running out of time. Okay, so to calculate that, okay, so you can actually do these expansions for this because you want to integrate over time. And this sigma AUA just comes out from a change of variable. But if you do it for the scalar, okay, so remember you just have to integrate your Green's function. So if you integrate this over sigma, okay, your delta function will integrate quite easily. You just have to change your tau integral to the sigma integral, and that's where this comes in. And then you have your tail term here. So all we're doing is taking the solution and integrating it. And that's what it looks like for scalar. Electromag, you have basically more indices, so it gets a little bit more complicated. And gravity's even worse. And this is kind of like the 3D version of what you have. You have your advanced and your retarded point, and it's in this area here where the field point is connected space-like that you're calculating or integrating over these. And then these tail terms can be done by Hadamard extensions. Okay, that's the general idea. I won't go into to solve for these. You can just do these massive expansions and then you throw them into formulas, and you just solve for your unknown coefficients, but don't worry about that. What it looks like in the end when you calculate these things. So what you do is you want to calculate the singular field. We can calculate it analytically, and then you just have to subtract it. So, but what it looks like when you do these big expansions, it starts off actually quite nice. And this is just, sorry, these orders now aren't orders. This is only for first order, but it's just saying this isn't how far you are away. So you say if it's a little bit away. So we're just expanding in the distance between the 2 points. And then it gets more complicated. So say you do the first 4 orders, this is what it look like. And then if you go to electromag, so it looks like this. So it gets even more complicated. And then you can imagine gravity is even worse. So the idea just being these things, they grow fast, which is why they're quite hard to calculate. Okay, so sorry, this should have appeared later. Okay, so let's actually talk. So once you get your singular field, that's great. Now you want to calculate your subforce. You want to calculate your like just that snapshot, how much you're coming off your geodesic. And there's several ways of doing that. And what's nice about the self-force program is there's 3 main methods, and they're all at different phases or different parts of development. But every time a new development happens, we can cross-check and make sure it agrees with the others. So the first proposed method of actually calculating these, and possibly the most powerful, is called matched expansion. And there what you have is, like I said before, you have your singular field like this and the retarded field. So your regular field is just, you take this, subtract this from this. But when we calculate the self-force, what you end up actually integrating over is just below the retarded time. So forget, this is a bad diagram show here. Forget about this second point here. That was just for field points to calculate singular fields. If we just focus on the world line, okay, so say this is the world line of this guy. We know that I have to, if I want to calculate the self-force, I have to integrate over the regularized Green's function down past this past line. But if I say I just want, it turns out the self-force, you just need it after this sigma point. So when you integrate, you're just starting off a little. So the only part that you really need is you're really just integrating this part of the retarded function. So even before they established how to do the singular, how to do a real clean singular split, you could just be like, okay, well, my self-force, I can just calculate it by integrating over the regularized from kind of just past the present point. And this will just be the V part. And the V part can be calculated via these Hadamard expansions. But only locally, right? So you have this normal neighborhood. Okay, so these things can only be calculated locally via the Hadamard expansions. But you are integrating, sorry, this should have been a minus infinity. You need to integrate over to minus infinity. So when people first started thinking about self-force, they're like, okay, we have to integrate the Green's function, not necessarily regular, there's a retarded one. Turns out they're the same. From just a moment ago, they wanted to avoid the singularity, but all the way down to the past. So what you can do is you split your integral. Locally, you can do Hadamard expansions. And then when you go into the distance past, you can use things like quasi-normal modes, you can do branch cut integrals into complex complex plane decomposition. It's very mathsy, it's very complicated, but people figured out how to do it. And the first time this was actually done, it's only done for the scalar case in Schwarzschild. They managed to calculate this, and this is done semi-analytically. So you do these with expansions. So the reason why I say this is a very exciting way of doing self-force is because it's solely semi-analytical. So you get that snapshot, just how much you're pushing off your geodesic in an analytical expression. Of course, you have to expand a lot. I think it was up to 52 orders to get this result here that they did for Schwarzschild. But basically, the local part here is in the red dotted line. And then the quasi-normal modes and the branch cut integrals were done here. And you see this, they pick a time where it's smoothly overlapping. And you just match your expressions, stitch them together. Okay. So this was done for Schwarzschild scalar in 2013. I wanted, and it was done with, I think, 52. So we actually have gone back to this recently. So this is unpublished. And we've gone up to V14 and we're getting closer and closer, but not quite where we want. So when I look at the error between the two expressions, we're at a good accuracy till about 20, t equals 20. And to match the analytical expressions, I think we need to push out to 25. So we're not there yet, but it looks like we're going to have this. This was just all done on my laptop as well. So what I'm doing now is going to run this on a server. And we're hoping to push this out more. And then we will have the first curve scalar match expansions, the first order. And like I said, completely analytical. Okay, so that's exciting. And I'm running out of time. Okay, so I'm not gonna, I'll just talk about, okay, so the effective source, what they do is numerically solve for the regularized field. So you have, again, you have your retarded equals your singular and your regular. So here what you do then is, okay, well, when I'm away from the little black hole, I know my singular field isn't in play. It's just a homogeneous box phi or is equal to 0. When I get closer, I do have to kind of compensate for that. So you do have box of the singular field in there and a delta function. And then you solve this numerically. So my point in showing this is you actually still need that singular field. But because the singular field expressions are so ginormous, sometimes we give the first few orders and they solve this wave equation, and then you try to even do more regularization afterwards. I won't go into too much of this. I'll explain this kind of diagram later for the mode sum, but this is just showing how if you have higher orders of the singular field, if you know your singular field to more accuracy, your when you're doing your L or M modes, they'll converge faster. So effectively you get more accuracy for less modes. Okay, and then the last thing I want to just show, the other way we do it is the mode sum, and this is literally you just do a spherical harmonic decomposition and you subtract mode by mode, because the whole thing is you're subtracting an infinity from an infinity. That's complicated and messy. So a lot of these different methods is trying to figure out how. So the first one, you don't have to worry about it because you're just solving directly analytical expressions. But the second one and this one, you have to numerically solve for the retarded, or in the other one, you're numerically solving the wave equation. And then you have the analytical expressions for the singular field, which you subtract. And to keep a handle on subtracting infinity, you do it mode by mode. There's a bit of sensitivity to this that you want to kill your M mode. So you kind of pick a coordinate system that will help you and put the particle or the small baby hole on the pole, because I'll kill your sum over M here. There's you can choose a delicate Euler rotation to make sure this integrates out very nicely. I won't go into the details, so you don't have to worry about any of this, just to say that you do come into problems when you try to do that integration. So we pick a coordinate system and kind of reverse engineer our Euler rotation to kill off those problematic terms. Okay, and then basically this is the idea. Similar to the other one, and I'll explain it in a little bit better. So this is the accuracy of your self-force, and say these are your modes. And you can think of these higher modes are way more numerically expensive. So Zach Nezepak actually did the numerics of calculating the retarded field. And then I get the singular field and he subtracts it mode by mode. And what you see here is when you just have the first two modes, you can kind of think of it as if I wanted an accuracy of just better than 10 to the minus 5, which is kind of what we need. Here, I need way more modes, right? But if I have a higher accuracy of the singular fields, that's what these A, B, C's are. It's just how accurate you have that singular field. And I subtract them mode by mode, and I want to get that same accuracy. Now I only need 9 L modes. And these ones are way more expensive. So in calculating the self-force, what happens is, and I asked Zach, he was saying what took to get the same accuracy, what took a week now took a day. So this is why part of the self-force program is taking care of these singularities. And I think I'm out of time. So I am just going to, I thought it'd be funny to show you what it looked like. This will take a moment to load. I don't know if you can see that, but that's actually the expression that the singular field is to get that that jump in accuracy. So they're very large expressions, which is annoying, but they're hugely useful. So that's why we do them. And there's even more. Okay, so it doesn't matter about any of this or this. This is just toolkit stuff. And I'll just end here. Sorry, I'm just passing through this because we're already over time. This is just saying anyone who wants actually to use some self-force tools, there's this thing called the Black Hole Perturbation Toolkit. A lot of stuff is on there, but it does pump out really nice geodesics, and it's also linked into that fast EMRI waveform, so you can actually play with waveforms. And then, as I'm saying, I have to always give this thank you with all of my funding bodies. So sorry for going a little bit over, and I'll end there.
Okay, so thank you so much, Dr. Heffernan, for a very nice talk. So we can now have some questions and answers. So if anybody has a question, kindly go ahead. Yeah, you can raise your hand and ask, or you can just directly ask a question.
So I will ask a small question. So I just got a little bit lost at some point. So when you are saying, when you are showing the graph of matching this asymptotic match, some point. So this is match with what? So I didn't actually follow it.
Oh, yeah, sorry. I know I was trying to, I could see I was running out of time, so I sped up, which is the worst thing you can do. So basically this is, so if you want to solve for the self-force via the Green's function directly, basically the self-force can be calculated by just integrating over actually the retarded Green function. And so you're just integrating over this tail part. And this tail part, you can get these Hadamard expansions locally. So this was the part that I did. But also you can do these like branch cut integrals to get the past distance. So this was first suggested in the 90s, but no one really, actually this was the real problem. They couldn't figure out how to do it. And then Mark Cassell got obsessed with it and eventually figured it out. So the idea is you're actually, what we're calculating here is the Green's function. And we're trying to match a local expansion, which breaks down as you move further down into the history. But at that point, you have these branch cut integrals, or you can do quasi-normal modes. And we also calculate this numerically to make sure. So here it's analytical, but here this matching, this is numerically calculated just to make sure that my expansions are matching. But on the other hand, we have these integrals that also match to this. So that's why I was saying I really need to push to higher orders to get a better match further along the timeline. So I could actually match with the branch cut integral, which is done semi-analytically, because then you would have a fully semi-analytical expression. And once you have that expression, all you need to do is integrate over it over time, and you will get your self-force. And when I say get the self-force, I mean, well, first order self-force, but it's literally that snapshot of how much you're pushed off that geodesic in that one moment. And then obviously you have to do that for every point on your orbit, depending on the resolution. That makes sense. And then what I had here is just the accuracy we were obtaining when I'm subtracting these two, relative error. And we're getting a relative error of about 1% out to 20 seconds. But we really need that out to about 27 seconds. So we're not there yet for it to be fully semi-analytical, but we have it matching with some numerics, so we know it's correct. We just have to push to higher orders to get the fully semi-analytical expression.
So this is the self-force expression. So now you have a perturbed geodesic equation. So you calculate the force, the perturbing force. Now to generate the waveform, you have to solve the geodesic elements, right? That's the next step. What you shown is the self-force part, but how do you go from the
Yeah. So that was what I was talking about here. So you can kind of think of these forcing terms.
Mhm.
So if you think of your GD, how your Kerr GD6 work, to actually evolve the waveforms. So there's these near identity transforms, these techniques that were used earlier, or smoothing over the orbits. So there's a few different ways of doing it. But the current state of the art then is obviously this multi-scale waveform. And these forcing terms is literally these are coming from the self force. And then these will give you your phase frequencies. And then all that will fill into your waveform here. So the self force has mainly been focused on just calculating these F1s for about 20 years, and recently F2. And again, I'd say it's only in the last 7 or 8 years we started looking at actually, once you calculate the self force, how do you evolve it? And there's this multi-scale waveform that's kind of become the state of the art.
So it looks like this part of Kepler problem. So people used to calculate these oscillating elements. So it's just part of the.
Yeah, people, that was the first ways, the oscillating GD6 kind of jumping from orbit to orbit. So that was the way people went forward.
Just to check, what is the current status of generating this waveform using the self force? So you have shown.
So the evolved waveform. So adiabatic is pretty taken care of, even though it's kind of weird. So all the pieces are here for some of these, but no one's actually written it up into a nice package. So if I go back here, when we say the fast EMRI waveforms, this is all available for Schwarzschild, it's all there. And then for Kerr, I think they use a 5PN. They do a little, like, it's not fully self force, but the ingredients are there, so it can be developed. It's just someone hasn't actually put it all together, but all the ingredients are there. But right now, I think up to a centricity of 0.5 or something, you have Kerr, and then circular and eccentric Schwarzschild are pretty well developed. So all the ingredients are there, but they're not all completely wrapped up in these beautiful packages yet, because that of course takes time, right? But Michael Katz has been putting a lot of work in that, and Alvin Chua and Niels Warburton and several people. So for the adiabatic, for the post-adiabatic, for the first order, it's pretty nailed down for Schwarzschild, but Kerr, not so much. I mean, this generic Kerr, this was one calculation done in 2017 by Martin Vandement. And he did it with Mathematica, so it took months to run. So we don't have generic evolved waveforms yet. So the full waveform right now is just for circular. So this one that I showed at the very start, this waveform here was Schwarzschild circular. And this is the full waveform to the accuracy to do parameter estimation and data analysis. So that's only for circular in Schwarzschild. But you have the lower order one, which is not as good, but can still be used to, like, people use it all the time to do astrophysical studies and stuff like this. So the adiabatic one is used a lot in science, but it's not, and it's good enough for detection. So you would detect it using it, but you just wouldn't get as clean or good parameter estimation for that. People believe you need the post adiabatic, which has this second order self force, which has got a lot of work to go yet.
So in the perturbation series, for the extreme mass ratio case, the perturbation parameter is the mass ratio, right? I mean, in the order, I think. And you said, point in the beginning that this can be somehow extrapolated to not so extreme mass ratio to some.
Yeah, so this was that first second order calculation that came out here. This is it compared to numerical up to this point, for a mass ratio of 10, which you wouldn't think would match that well, but they matched it up to an SXS. And you did see some phase differing then. But for like, they weren't expecting it to match as well as it did. But this is the self-force waveform over an SXS waveform. And you see some dephasing towards the end. Which is highlighted here, but it was matching very, very nicely. So that then started making people realize we would be able, like, numerical relativity is obviously better at Q equals 10, but like if you go to Q equals 40 or 100, where numerical relativity really has issues, this would give you confidence that the self-force is capturing it. And then there's a few people like BJ and Scott Field and stuff who have been trying to do that, extrapolating from self-force calculations down to post-Newtonian and numerical relativity waveforms and trying to bridge the graph very smoothly. And they've had some very nice results as well. So it does look like combining numerical relativity, PN, and self-force will be possible to nicely cover that gap that people weren't entirely sure about.
No, is there like at least for the extreme mass ratio case, is there any like a time scale naively after which we really need the NR simulation self-force will break down, something like that?
So at the moment, sorry, you mean like timescale as you're going towards merger and plunge?
Maybe
yeah, so at the moment, we've been focused on the in spiral because EMRIs are extreme mass ratio in spirals, but some work has been done recently on the plunge, and there is no theoretical reason why self-force should not work for the plunge and merge. So, and also then after the plunge, once you have the plunge, right, you can go into quasi-normal modes. But basically, as of now, people don't think there's nothing in the approximation that says it would break down. So people have started looking at that, and they're not there yet, but they've already got some nice results and comparisons for like these lower mass ratios. So at least they can compare to like Q equals 10 simulations of numerical relativity and just see if it at least looks like it's kind of matching, and they have something. So none of that's published, but there are people working on it. And yeah, but I mean, you'll still need numerical relativity to check, especially when you're kind of going into these mass ratios of 10 or 15.
Thanks.
No worries.
Okay, any more questions? Okay, so if not, let's thank Dr. Heffernan again, and thank you very much for a very interesting talk. So I'll now hand this over to Arpan.